Welcome back, class. Today we'll be discussing how we write out the FFT equation. But to begin, let's start off by reviewing the DFT equation, as you all probably have seen. This particular equation can be written in many different formats, and the one seen here will be the one used in computing the FFT algorithm. And one thing to note would be that this is a summation of your input signal times by e to the negative j 2 pi kr over k. The two k's in this case aren't the same. The k you'll see in green will be referring to however many point radix in relation to the FFT that you'll be doing. You'll notice that the R is related to the DFT sample number you want to take, as if you wanted to take the 5th sample of your DFT. That would be the R in this case. So you'll notice our summation goes from 0 all the way up to our k minus 1. In all of our videos, this k will be denoted with a green k. So, in this particular example, we'll be using a radix 2, and to do that we have to break down our components from our sample into even, and odd sample. And these samples come from the actual input signal. Okay. And the next step that we'll need to write our FFT equation will be to write out a twiddle factor. And what this is it's a replacement of a variable in our DFT equation. If you look back up here, we'll take this whole term up here from our previous equation. I think I'll try to draw it out for you. Excited. Okay. Let's get rid of that. So you'll notice that the green K that we have is always going to be referring back to the point radix that you'll be using is transferred over. And in this example, in our unit circle, we drew a 4-point unit circle for you, having DTF sample 0, 1, 2, 4 as I just labeled. You'll see that the twiddle factor on all of them, the green K, since it's a 4-point, is 4, and then the top R relates back to the actual sample you want to take of your DFT, that is. Okay, so now that we have that common understanding, let's move over to our actual decimation in time of our FFT. So we'll be taking all of this information we have over here, our even and odds and our twiddle factors, and we'll write it all down in an equation for our FFT algorithm. Let's zoom in real quick so you guys can see this a bit better. So here we have x of r is equal to g of r, and I'll be really careful to use all these colors to match up throughout all of our videos for even, twiddle factor, and odd, red, green, purple. So our g in this equation above is actually just all of our even components of our DFT. So we'll just be summating only the even components. And nothing else on the actual DFT equations changed. And the way we get these components is we set them equal to 2 times m, m being the number pick we would like. Then we'll move up here and we'll define our h of r in our equation above. That's going to be equal to all of our odd components of our DFT. And you'll notice that our odd component, you still have to multiply by a total factor. And I'll explain that here in a moment. But the way that we calculate up our k's being only odd, we use the equation k equals 2m plus 1. So let's go back over here and we'll briefly explain why our even components don't have a total factor, but our odd components do have a total factor. And the reason for this goes into complex conjugate symmetry of the signal. Let's zoom in over here. We still have our equation from before, our even components, our total factor affecting our odd components, being our W1 of 4 and W3 of 4 being a 4 point. So I'll go ahead and write down why on our even components we're not going to have a total factor. So our even components would be W0 of 4 and W2 of 4. And you'll notice that since they're complex conjugate of each other, they're just going to be equal to the negative of each one another. And if you refer back to our unit wheel for our 4 point, that's where we got our actual values of these, being 1j, -1, and -j. I'll finish writing out these for you guys. Oh, sorry. That's, never mind, I got it right. Equal to a -j, -w to the 1 of 4. Think. So I'll go back over here for just a minute on you guys, and I'll explain to you that the reason we lost our total factor on our even components, referring back over to our unit circle, we only have real components on our even, being 1 and -1. So when you actually write those out to multiply them, that total factor cancels, because, well, I wouldn't say it cancels, it just becomes a 1 or a -1. So there's no need to multiply a imaginary number into it. And we'll discuss some more about this in our later videos. See you soon.